Let's walk through a classic titration experiment, step by step, with a numerical problem you're likely to see on an exam. Step-by-step solved example, the EDTA titration. All right, grab a pen and paper. Here's our problem. This looks like a lot, but we're just going to break it down. The whole process has two main phases. First, we figure out the true strength of our EDTA solution. And second, we use that information to test our actual water sample. Let's begin. Phase 1. Standardization of the EDTA solution. Step 1. What is standardization? Think of this as a calibration step. The EDTA solution we made might not be perfectly accurate. So before we test our unknown water sample, we test our EDTA against a solution we know the exact hardness of. This is called a standard hard water solution. We prepare it by dissolving a very precise amount of pure calcium carbonate, our reference chemical, in distilled water. In our problem, we're told this solution has a strength of 1 milligram of calcium carbonate per milliliter. Now we titrate this known water with our unknown EDTA solution to find the EDTA's exact molarity, or strength. Let's do the math for our problem. We'll use the classic formula M1V1 equals M2V2. Here, M stands for molarity or strength, and V stands for volume. The strength of the standard hard water, M2, is 1 milligram per milliliter. The volume we used, V2, was 20 milliliters. The volume of EDTA we used, V1, was 25 milliliters. The strength of EDTA, M1, is what we need to find. So, rearranging the formula, this gives us M1 equals 0.8 milligrams per milliliter. What this means is that 1 milliliter of our EDTA solution is exactly equivalent or can neutralize 0.8 milligrams of calcium carbonate. This is our key. We've standardized it. Phase 2. Titration of the sample water. Now that we know the exact strength of our EDTA, we can confidently test our actual water sample. Step 2. Take a water sample. First, you use a pipette to measure out an exact volume of the sample water into a clean conical flask. For our problem, this volume is 50 milliliters. Step 3. Add the reagents. Now, we add two crucial chemicals. First, a buffer solution, usually ammonium hydroxide and ammonium chloride. The only job of this buffer is to keep the pH of the water sample at around 10. This is the perfect environment for our indicator to work correctly. Second, we add a few drops of our indicator, which is usually Erychrome black tea, or EBT for short. As soon as you add the EBT indicator, it finds the calcium and magnesium ions in the water and forms a complex with them. This complex has a very distinct wine red color. If your solution turns wine red, you definitely have hard water. Step 4. The titration. Now for the main event. We fill our burettes with our standardized EDTA solution, the one we know has a strength of 0.8 milligrams per milliliter. Then we start adding the EDTA solution drop by drop into our wine red water sample, swirling the flask constantly. Here's the chemistry happening. EDTA is a chelating agent. You can think of it as a claw. It is much better at grabbing onto calcium and magnesium ions than the EBT indicator is. So as each drop of EDTA enters the flask, it rips the metal ions away from the indicator. Step 5. The end point. You keep adding EDTA until all the calcium and magnesium ions have been grabbed. The very next drop of EDTA will pull the last metal ion away from the last EBT indicator molecule. The moment the indicator is free and alone in the solution, it instantly changes color from wine red to a sharp steel blue. That color change is your endpoint. You stop the titration immediately and note the final reading on the burette. In our problem, this volume was 18 milliliters. Final calculation. Now we just need to calculate the hardness. We know that 1 milliliter of our EDTA solution is equivalent to 0.8 milligrams of CaCO3 hardness. And we used 18 milliliters of EDTA to neutralize our 50 milliliter water sample. So, the total hardness in our sample is simply our 50 milliliter sample contains a total of 14.4 milligrams of hardness expressed in terms of calcium carbonate. But the question asks for the answer in parts per million, or ppm. Remember, 1 ppm is the same as 1 milligram per liter. So we need to figure out how much hardness would be in a full liter of this water. If 50 milliliters of water contains 14.4 milligrams of hardness, then 1,000 milliliters, or 1 liter, would contain, and since milligrams per liter is the same as parts per million, and that is our final answer. By following the procedure, we've successfully measured the hardness of our water sample.